Okay, let's look at the next example, please. Consider f, well, actually, as long as x is not 0, it's not really that weird at all. Consider f of x equals x squared times the sine of 1 over x. We showed earlier that f, longhand, by pushing limits, that f prime of 0 equals 0, or well, actually, we could use the squeeze theorem. That's right. So we can do the squeeze theorem. Could we have used the shortcut chain rule at x equals 0? Can you use the shortcut methods? You can use them everywhere else, but can we use them at x equals 0? No. However, the answer, of course, is yes for any other point. Indeed, for non-zero x, we just do the chain rule. If we derivate the x squared, remember, well, we do the product rule and chain rule. I need to be careful. We're using, I really should say chain rule and product rule. Because, and power rule. We're using a combo, but I'll just leave it at chain rule. But we're really using the chain rule, power rule, product rule. We're using several rules, as long as x is not 0. Now, if x is 0, we have to use a squeeze theorem. We can't do any of that. So first, for x not equal to 0, guys, recall f of x is x squared sine 1 over x. So if we do by the product rule, we'd have we derivate the x squared, leave the sine alone, and then plus we leave x squared alone and derivate the sine. So that's the product rule. That's kind of the guy that's going to get us started out. So we derivate x squared, and I don't need this times sign here, really. So I have 2x sine 1 over x. There's nothing wrong with it, but I just don't need it. And then plus, now be careful, we leave x squared alone and we derivate the sine of 1 over x. Now by the chain rule, we derivate this interior and get negative 1 over x squared. And then we derivate the exterior only and we get the cosine of 1 over x. Again, we let u equal 1 over x, okay? Now remember, you go through the motions of the chain rule, you let u equal 1 over x. And you would get, for this part, I didn't want to go through all that, but you would have x squared times all that. But a better way to do it is just to say, look, derivate the interior, you get negative 1 over x squared. Derivate just the exterior, and you get the cosine of 1 over x. Guys, just do that. Save yourself some torture. Okay, and you remember, you're out, well, Jason, how did you get from here to here? You remember when I derivated, if you derivate 1 over x, remember, guys, you're derivating x to the negative 1 power, and by the power rule, the negative 1 comes down, and you get negative 1, which x to the negative 2. That's just negative x, the negative of x to the negative 2, but that's negative 1 over x squared by the power rule. That's how I got this guy right here. By the chain rule, I had to derivate this to get this. By the chain rule, I had to derivate this, and to do that, I had to do the power rule, so I got this. And then I derivated the sine, but by prior results, we know that's a cosine straight away. So there's that. Now, hey, we're adding a negative, so that's just the same thing as subtracting. And this time sign here is okay, but I don't really need it. So I have 2x sine 1 over x minus a cosine of 1 over x. Yeah, guys, again, to get, when you derivate the sine of 1 over x, by the chain rule, you derivate 1 over x, which is x to the power of negative 1, and you get negative x to the power of negative 2, but that's negative 1 over x squared here. That's okay, so there's that. And then you derivate just the sine part, and you get just the cosine of 1 over x. Okay, chain rule going on there. Now, if you had tried to plug 0 into this, you would get 1 over 0. You'd get 1 over zeros in the sine and cosine, which we cannot do. You have to, for the x equals 0 case, you can't even do this. You have to go back to the original. You have to go back to f of x itself and do the squeeze theorem, and you'll get f prime. It does exist. You'll get 0, but you have to deploy the squeeze theorem to get it. Now, what? Let me just show you what I mean by that. To get, now, remember, we go the old-fashioned route. I type in my limit, so I do the limit. Now, for the 0, I'm doing the 0 case. So I'm going to show you that f prime of 0 does exist, and that it does equal 0. So that's the limit as x goes to 0 of, well, remember, we do the difference quotient. I do f of x minus f of 0 over x minus 0. Now, guys, f of 0, we defined it separately. I need to be careful about something. We've got to define f of 0 separately. We define f of x to be x squared sine 1 over x for non-zero x. But we define f of 0 to equal 0. That's crucial. I have to put that. And I'm sorry about that, guys. I'm sorry I left that out. That is crucial, and that does need to be put. So let me see if I can't shrink the font just to get all this on one line. Is it not? It's not going to let me. Okay, so it's not going to let me. It wrapped around the line. I'm sorry about that. So we consider the function f of x equals x squared sine 1 over x for non-zero x, and f of 0 equals 0. We're defining just from the beginning. We're defining f of 0 to equal 0. Okay. Now, we've actually already showed from previous videos, we've already showed that f prime of 0 equals 0 by using the squeeze theorem, and I'm going to remind you of that down here. How did we go about doing that? Because you might be rusty. So remember, this is the definition of the derivative at 0 if it exists at all. We need to show that it does. So the limit of that, so that's the limit of, again, x goes to 0. Now on the bottom, x minus 0 is just x. Now f of x, we define that to be the sine of 1 over x. Okay. No, wait, oops. No, we don't. We define that to be x squared times. My bad. We define f of x as x squared times the sine of 1 over x. Now we got that x on the bottom, but it's no big deal. We're still inside the limit. So this x squared divided by x is just x. We divide this x off this x squared here, and we're just left with x times the sine. Not for just to make it look pretty, I'll put the times sign there. So it's x times the sine of 1 over x. Oops, in the limit. Gotta have the limit. Gotta have the limit. Okay, so the limit of that. So excuse me. So limit x goes to 0 of... come on now. I'll need the parenthesis because I don't have the denominator just because of aesthetics. So there's that. Come on. Be nice. And no, be nice. All right. It skipped a line, but it may just have to be. Okay, there it is. So this x squared divided by this x leaves you with just x itself. But now by the squeeze theorem, remember, x times the sine of 1 over x, that's caged between the neg absolute value of x and just ordinary absolute value of x. But the limit of both of those guys goes to 0, and since x sine 1 over x is caged between, it goes to 0. So, but that we have no choice but to conclude that equals 0 by the squeeze theorem. And let me move this other junk down here. Okay, and to be honest, this should not be capitalized, and squeeze theorem should be capitalized. But anyway, my grammar is getting unwieldy. So there's that. Guys, I hope that helped. And again, remember, by the squeeze theorem, x times the sine of 1 over x is the sine cannot go above positive 1 or below negative 1. So x times the sine of really whatever is caged between negative 1 times the absolute value of x and just the ordinary absolute value of x. But those two absolute values, they both limit to 0 as x goes to 0, so that this guy in the middle has no choice, since he's continuous, and he has no choice but to go to 0. Well, actually, never mind him being continuous. Even if he wasn't continuous, never mind. He has no choice in any event, continuous or not. He must go to 0 because there's two continuous guys on the extreme left and extreme right that are going to 0. You know what? Forget continuous. There's two guys on the negative 1 times absolute value of x on the extreme left, the ordinary absolute value of x on the extreme right. Their limits are tending to 0 as x goes to 0. So x times the sine of 1 over x himself, that limit must tend to 0 as well. Okay, and thank you guys. We'll move on to the next video. Bye-bye.